Hola, la clase de biología. Okay, welcome to yet again another screencast. This one is called Energy and Thermochemistry. And if you took chemistry last year, this is going to be a bit of a review for you. And if you were paying attention in our class earlier on in the year, this will also be a review for you. So this could potentially be a review of a review. But it's good. So we're going to be talking about energy and thermochemistry, and essentially when you break it down, we're going to be talking about chemical reactions. And in biology, chemical reactions are very important because chemical reactions essentially are just the making and breaking of bonds between molecules, so either building things up or breaking things down. And so we're taking chemicals and we're breaking them down to basically extract the energy contained within those bonds, or we're using them to create usable chemicals. So in sum, all the chemical reactions in your body are called your metabolism. And your metabolism can actually be broken down into those two different processes. So the breaking down of stuff is called catabolism. Again, this is breaking down. And so we've got metabolism, which is made up of catabolism, and also anabolism, which is the building up. So, metabolism, not just breaking down nutrients, but also building up organic molecules. Okay. And there are actually two major processes that we're going to be talking about in great detail over the course of the winter term. One is a catabolic process, and the other is an anabolic process. Oh, and the way that you can think about these two to remember them, at least the way that I remember them, if you're taking anabolic steroids, you are building up muscle. So anabolism, building things up, anabolic steroids. Catabolism, just remember it because it's not anabolism. Okay, but going back to what I was saying before, the two processes that we're going to be talking about that are fundamental to all life on Earth, we couldn't live if we didn't have these, are, for anabolism, the building up, photosynthesis, and for catabolism, the breaking down, cellular respiration. And like I said before, we're going to spend the better part of basically a month and a half talking about these two things because they are so important, so integral to all life on Earth. But before we get there, let's talk a little bit about chemical reactions and how we can set them up and diagram them out. So, moving over to a new section right here and zooming in. So, start out with just a simple graph here, and let's put time on the x-axis. And think of this as the process of the reaction. Put that on one line. Okay, and on the y-axis we have energy. So for those of you in chem, you're probably used to seeing actually enthalpy on this y-axis, but it's just a little bit more simple and more clear in biology if we talk about energy. So decreasing energy going down and increasing energy going up the y-axis. Okay, and let's talk about a chemical reaction. So here are our products. Our reactants. 2H2O plus, just H2O. Water plus carbon dioxide goes to C6H12O6 plus O2. Okay, so for all of you folks listening out there, C6H12O6, very important chemical formula. This is glucose right here. So this is actually the chemical formula describing photosynthesis. And for all of you astute observers out there, you'll notice that it's not balanced. So to balance this equation, 6H2O plus 6CO2 goes to C6H12O6 plus 6 oxygen. Okay, excellent. And over here, on this side of the equation, these are our reactants. And over here, we have our products. And you probably wouldn't know this just by looking at these things, but I'm going to tell you because it's important for what we're going to do next, that the reactants in this equation are actually at low energy compared to their products, which are at a high energy or higher energy. And so to be completely, I guess, honest isn't the right word, but we'd have to write plus energy on this side of the equation to get our final C6H12O6 and 6 oxygens on the other side. Because remember, the first law of thermodynamics tells us that energy is never created nor destroyed. Okay, so the energy that's input in this system comes from elsewhere. It actually comes from energy provided by the sun. Okay, so if we have our lower energy reactants and high energy products, we can plot them on our graph right here. We've got low energy reactants and then products which are at a higher energy level over here. And let's write them in below. This is H2O plus CO2 up here, and then our products are C6H12O6 plus O2. And if we were to look at our reaction coordinate diagram, we have to connect somehow our products to our reactants, or I should say our reactants to our products. And the reaction coordinate diagram is going to look something like this. You've seen this curve before. Voila. That's going to bother me. Let's see if I can line this up a little better. There we go. That's a little better. Okay. Muy bien. So now, if we take a further look at this graph, you'll notice that the difference in energy between the reactants and the products is about yay tall. And this is called delta H. And for this type of reaction, which is an endothermic reaction, delta H is equal to a positive number. We actually have to put energy in to this reaction to get it to go forward. So it's called an endothermic reaction. And yeah, that's all I want to say about that, actually. But you'll notice here, there's a little piece of the curve that is unaccounted for. And we've talked about this before. This is what is called the activation energy. Or you can call it E-fish, E-alpha activation energy. And it's the little bit of extra energy you need to provide in the system in order to actually form the products here. Boom, boom, boom. Okay, so we have got our endothermic reaction here, and I'm actually going to select this whole thing, just move it down a little bit, and what I want you to do is actually take this graph that you just made, and I want you to copy it, and then moving over to another part of your Notability, I want you to paste it in again, but this time you're going to go in and you're going to erase everything that you just drew. Okay, oh shoot. Okay, so now you have an empty graph, and you'll notice I took the chemical formula for photosynthesis and I flipped it around. So now what was the products are now the reactants, and vice versa. What was the reactants are now the products. And this is actually the chemical formula for cellular respiration. So here we're starting out with high energy reactants, and we're ending up with low energy reactants. Products. I don't know why I messed that up twice. Okay, so our products are low energy, our reactants are high energy. So in the process of going from our reactants to our products, energy is released. And this energy that's released can be lost as heat, or it can be used to do useful cellular work. Again, we're going to talk more about that later on in the year. But if we're to plot this out on our graph, we have to start with a high energy reactants and ultimately end up with low energy products. And again, this is C6H12O6 plus O2 over here, and then we end up with H2O, and which is water, and CO2, carbon dioxide. And connecting our reactants to our products, we get an energy coordinate diagram that looks something like this. Okay, voila. And again, we have a delta H here. But this time, delta H is equal to a negative number. Because, again, our reactants had more energy than our products, so the change in energy is negative number. And so this is called an exothermic reaction. Heat or energy is released. And once again, we have this activation energy, or this E alpha. And it's the energy required to get the reaction started. So, there you have it. Endothermic and exothermic. I hate it when you can't see the whole thing. Excuse me for a second. Okay, better. There you have it. Endothermic and exothermic reactions. And now really, this is ultimately the point of today's screencast, is to emphasize again what an enzyme does. So we talked about enzymes a little bit before, and you know that their structure is integral to their function, and I hope you recall that enzymes have a primary structure, which is the linear sequence of amino acids, which forms a polypeptide, and then those are in turn folded into secondary, tertiary, and quaternary structures, which give proteins their overall shape, and their shape informs their function. So remember, if we had an enzyme that looks something like this, the products are going to go, the substrate are going to enter into the active sites right here, and then the enzyme will ultimately change shape and put those substrates together in such a way that they are in the perfect position to undergo a reaction, a chemical reaction, and ultimately a product will pop out. I'm going to draw it in a different color to show that it's now a product. And again, the enzyme's shape is critical to its function. If you change the shape, then you can destroy or potentially change the function of the enzyme. And so enzymes work by lowering the activation energy of a reaction. So if we were to draw in a curve like this purple line, dashed line, would show us with an enzyme. And so, once again, our activation energy right here is changed. We lowered it. And likewise, in an exothermic reaction, we would lower the activation energy by providing an enzyme. Okay, so it's a little bit easier, I think, to visualize what's happening in an exothermic reaction, because if you imagine the activation energy being like if you were up here with a huge boulder trying to get it to roll down this hill, you'd have to push it up and over this big hump before you could get it to roll down, and it would, once you got it to this point up here, then it would just happen spontaneously, but you have to get up to the top of the hill. Now, providing an enzyme is like boring a tunnel through this hill. So then it's just easy to push the boulder and have it roll down the hill. It's a little harder to understand that with this, but I guess you could use the same analogy here. If you're trying to take a boulder and push it all the way up this hill, if you drilled a tunnel right here, once you got to this point, it would be easy to get it all the way up here. So I guess the metaphor or the analogy works both ways. Okay, but ultimately, this is it. And hopefully this is helpful, because we are going to be doing some experimentation with enzymes tomorrow. Okay, that is all. Have a nice night.